Okay, last time we considered sets, the very basics of set theory, and we stopped after considering this way, which we call the first one, this way of constructing a new set. If you are given with a few sets, finitely many of this, that is A1, AN, so on, you may construct this set using curly brackets. You can construct this set, which by definition has exactly A1, A2, and so on, AN up to AN as its elements. Formally, you may express this meaning in the following way. For each x is an element of this set if and only if x equals, so we say x is A1, that means x equals A1 or x equals A2 or x equals AN. So you can, that means that you can just group 1 or 2 or 3 or even one set. You may group them together and in particular, you may group one set with itself and construct so-called singleton. The singleton of the set A1. Is it clear? Do you have any questions concerning that previous material? So probably no questions. Let's continue. We want to consider another way. In fact, 3 more ways to construct a new set. And the second one is as follows. Assume that A is a set and phi is a predicate, some property. Then it is possible to take all and only elements of A which satisfy phi. So then there exists a set denoted the following way: all x's from A which satisfy phi, such that y is an element of this set. Please notice this complex notation which we use. For each y is an element of this set if and only if y is both an element of A and y satisfies phi. For example, this makes possible to construct a set of odd natural numbers. You may consider all natural numbers, all x's from the set of naturals, which are odd. X is odd. We have n is A, n is A here, and being odd as phi. So our property is just being phi. Of course, every number every y belongs to this set if and only if y is a natural number and y is odd. That is, y satisfies our phi. Clearly, this set is a subset of A. because every element of this set is also an element of A. This suggests the following name for this set construction principle: subset specification. So we specify this subset by property phi. So clearly, this set is always a subset of A. By the way, this very notation has its own proper name. It's called the set builder notation. The set builder notation. It is a very popular name for this construction, and in particular for the notation thereof. So, dear students, any questions, please?
No.
No. So, is it clear?
Yes.
And now, using this principle, that is that we may construct a subset in every given set with whatever property, we may explore the following possibility. And what if our property is contradictory? What if it is not possible to satisfy this property? For example, let's define the following set. The set of all naturals which don't equal themselves. What can you say about this set? Can it have any element?
No.
So, there is no natural number which is not equal to itself. So, formally, if y is an element of this set, then y does not equal itself. But we know, we have previously proved that every set equals itself. So we have a conjunction of a statement and its negation. This conjunction is always false. So we have got a contradiction, a falsity from this statement. You know that if from some statement it follows a falsity, then the statement must be false. So this one is false for whatever y. And we may thus conclude that for every y is not an element of this set. So that's not true. Y is not an element of this set. Interesting. By definition, a set E is called empty, or alternatively they say that it is void. So a set E is called empty, but according to the Russian tradition, I'll call it empty. A set E is called empty if and only if it has no element. So any set without elements is called empty. Corollary. This set is empty. as it has no element. But do we have any other empty set? Is it possible to have two or more distinct empty sets? What do you think? May two empty sets be not equal to each other?
No.
No, of course, but why? Let's prove an interesting property of empty sets. Do you remember the story about the present king of France? Namely, that the present king of France is bald.
Yeah.
And now we want to translate this story into set theory. It's very easy to do so. If E is empty, then for every set A, E is a subset of A. That means that every element of the empty set is an element of A. Indeed. This statement by definition means that every X, which is an element of E, is an element of A. Here we have an implication, but also we know that E has no element, so this is false. From a false assumption, it follows everything. So this implication is true for whatever X. So you may think about it that the set of the present kings of France, this set, is a subset of the set of bald people. It is the same. Why? Because this set is empty. So we see that any empty set is a subset of every set. Let's memorize it. An empty set is included into any set. As a corollary, we obtain the following. If E is empty, then E equals our exemplary empty set. This one. Why is it so? That's easy. You know, E is empty. This set is empty. An empty set is a subset of any set, so this is included into this one. And likewise, this one is included into E. From these two inclusions, it follows that the sets are equal. So, what does it mean? That means that there is a unique empty set. So empty set is unique, and this one might be rightly called the empty set, as it is unique. So it is the empty set. Yes, there is no other. Is it clear?
Yes, clear.
Empty set is very useful in formal developments. Why is it that useful? Because we know its elements for sure. We are guaranteed that it has no element. So its structure is known to us in every detail. We know, say, everything about this set. Another set construction principle makes not a lesser set a subset specification, where we take just part of our given A. We are given with A, and here we take a part of it. And the third principle goes upper, so it creates a greater set in some sense. The main idea is as follows. You may group together and consider the set all subsets of a given set. So this is called the power set, or the set of all subsets of A. So I'll call this axiom, this principle, the power set. Okay. Let A be a set. Then there exists a set P of A such that for every X is an element of P of A if and only if X is a subset of A. So P of A is a set. It is the set of all subsets of A. You may group together all subsets of A. Is it clear? It is allowed. So we have a principle that guarantees that such set indeed exists. Is it clear or not that clear?
What's the name of the set?
Power set. The power set.
Okay, thanks.
Whence P, the power set of A. Why power? We shall see it in a moment. At first, informally. First of all, let's see what is the set P of the empty set. Which subsets does the empty set have? Which subsets does it have? What is the subset of the empty set?
The empty set.
Of course. And anything else? Nothing else. So the empty set is the only subset of the empty set. Why is it a subset? You know, empty set is a subset of every set. Moreover, you may recall that every set is a subset of itself. Hence, the empty set is a subset of the empty set. Or equivalently, the empty set is an element of the power set. I want to prove that there is no other subset of the empty set. That's clear. Assume that some X is a subset of the empty set. What does it mean? That means that every element, or let it be not X, some other let it be, say B. For every Y, if Y is an element of B, then Y is an element of the empty set. But the empty set has no element. So this conclusion is false. From some statement, it follows falsity. May this statement be true? Of course not. If you have an implication which is supposedly true, but its conclusion is false. That means that its assumption must be false as well. So it is possible only when for every y is not an element of B. So B is empty. Yet we know that this set is the only empty set. Hence, B is the only empty set. So in general, we have that B is an element of this set if and only if B equals empty set. But of course, that means that this set equals singleton equals the singleton of the empty set. For here we have the same condition for each B. When this conclusion, is it clear?
Yes.
And what if we will consider some singleton? Which subset it has? A singleton.
Empty on itself.
Of course. Of course. Of course. Why is it so? Because we know that the empty set is a subset of whatever set. And also every set is a subset of itself. And these two are not equal because this one is not empty. And what if you take 3 elements, say 1, 2, 3? Which subsets will you obtain? As usual, the empty set, as it is a subset of any set. What else?
1, 2, 3.
1, 2, 3. Do you mean this set?
Yes.
Of course. What else?
1, 2,
not
3.
1, but the singleton of 1.
Yes. Singleton of 1 and 2 and 3.
What else?
1 and 2. 1 and 3 and 2 and 3.
And 2 and 3.
Yes.
Okay, and now let's informally count them. How many elements do you have here in the empty set? How many elements informally?
0.
0. And in this singleton?
1.
1. 1 equals 2 to power 0. How many elements do you have here?
1.
And here, you know these two are not equal.
Yeah.
2 elements.
To the power of 1.
Here you have 3 elements. And here, 1, 2, 3, 4, 5, 6, 7, 8. And here, you have 2 to power 3, 8 elements. And what if you take just 2 elements? What are the subsets? So please name them.
Empty.
Empty.
1.
2 singletons, of course. And the set itself. So here we have 2 elements, and here 8, that is 2 to the power 2. So is it now clear why this set is called the power set?
Mhm.
In a finite case, in the finite case, it has 2 to the power n elements if this set has exactly n elements. And of course, there remains some meaning of this power in the infinite case. Okay. By the way, you may quite beautifully depict these sets in a diagram. Namely, this set is a subset of both singletons. It is a subset of both these singletons, while these two are subsets of this one. Of course, the empty set is a subset of this set as well, but there is no need to draw an arrow, as it follows from transitivity that if x is a subset of y and y is a subset of z, then x is a subset of z. So here you obtain a square. And in the case of 4, of 3 elements of 8 subsets, you may got a cube. So here you have the empty set. This is 1, 2, 3. 3 singletons. 1, 2, 3. Here you have a superset of these 2 singletons. That is 1, 2. Here 2, 3. 1, 3 is behind. So such a cube. Is the principle clear?
Yes.
Okay. In general,
Is it possible to show the diagram for four?
Of course. It would be a plane projection of the 4-dimensional cube. Of course, you may try draw it. It's quite interesting. Try drawing it. Okay. And the last set construction principle we want to consider. It is not the last known to mathematics, of course, but it is the last we want to consider. This is the principle of union. The union. We will consider somewhat restricted form of this principle. Because it's easy to understand. In a restricted form, it says exactly following. Let A and B be some sets. Then there exists a set A union B. Or they also pronounce it A join B. A union B. There exists a set A union B such that I'm sure you already know this set. X is an element of the union when? X is an element of what?
X is element of A or X is
or
element of
X
B.
is an element of B. That's it, exactly. Of course, if you can construct, now let's consider an example. What is the union of these two sets? Which elements it has?
1, 2, 3, and 4.
Of course. If you may construct a union of two sets, it's possible to have a union of whatever finite number of sets. Say if you have three sets, you may define the union of three sets the following way: the union of A and B, union C, and so on. For n sets, it is just A1 union A2, union A3, and so on. A little bit later, we shall see that the way you group them using parentheses just does not matter. So this is a restricted form of the union principle. And now I'll show you the general form, but formally this won't be a part of our course. So the general form. The general form is as follows. So let's mark it with a star. Let A be a set, then there exists a set union A. Now union means a unary operation. There exists a set union A such that for every X is an element of A if and only if there is some Y such that X is an element of Y and Y is an element of A. So informally, that means, here we have a union. X is an element of the union of Y if and only if X is an element of an element of an element of A. This is the main idea. This way, you may easily obtain our binary union as follows. A union B is just the union of this set. So, what does it mean? That means that if A consists of some set C1, C2, say C3, C1, C2, C3, of course, what is the union? The union of A is a set of all points, all elements, which each of which belongs to at least one element of A. Is it clear? So probably it is indeed too abstract, as apparently you don't want to say anything about this thing. Okay. Let's leave it in peace and focus on this restricted form. Let's understand union as a binary operation, as in the high school. Now, we may define two more binary operations which are also should also be familiar to you very well. The intersection of A and B, or the mid of the sets. The intersection or mid of A and B. What is it? What is the intersection? May you define it in terms of our set construction principles? Can you define it using our set construction principles? As a hint, I suggest you use the second principle.
I think A has an intersection with B if
the set
there
of
is an
all x, where from? From A, which are also elements of B. All elements of A, which are elements of B. Clearly, for each x is an element of this set, if and only if x is an element of A, and also x satisfies our condition, x is an element of B. As a corollary, we obtain, as we know that this is equivalent to this one. As a corollary, we may obtain that the intersection of A and B equals the intersection of B and A. Is it clear? So the intersection is a set of common elements, of all common elements. You take A and then pick every element from A, which is also an element of B. That's the main idea. Is it clear?
Yes, thank you.
What's next? Another operation is set difference or set minus, A minus B. A minus B. What is it? The same idea in defining it. All elements of A which are not elements of B. A without B, or A minus B. We may group together all elements of A which do not belong to B. Is it clear?
Just please explain it again.
What do you want me to explain again? This
A-
definition.
Yes, yes. Please.
This is A minus B is by definition, it is the set of all and every elements of A which don't belong to B. Just take all elements from A which don't belong to B. Say, you may take all natural numbers which don't belong to the set of 2 and 4. What is it? X is not an element of this set. What does it mean? It is the set of all naturals except 2 and 4.
Thank you.
Or alternatively, you may use this set minus operation. Naturals minus this set. So if you this operation is useful when you want to exclude some elements from your set. And now let's explore some simple properties of these operations. Lemma. I say that the intersection of A and B is a subset of A, and A is a subset of the union. Is it clear? Why is it so? Because if X belongs to both sets, it of course belongs to A. And if it belongs to A, of course then this disjunction is true. It belongs to either A or B. Is it clear?
Mm-hmm.
The same for B, of course. A minus B is a subset of A. That's also clear. It is a set of all elements from A which do not belong to B. And the last property is that A minus B, if you intersect it with B, you will obtain what? Which elements both belong to B and does not, and do not? No elements. This is the empty set. Is it clear?
Of course.
By the way, we say that X and Y are disjoint, if the intersection is empty, if they have no common element. So A minus B and B are disjoint. And now let's prove something more interesting, and namely the following fact. Let's call it lemma 1 and our lemma 2. So, what is the question?
Yes. Is it possible to write minus like negative, or we have to write it like
This way. This way.
Yeah. Yes.
Of course you can, but I prefer this form. That's up to you. The only thing you should guarantee that everybody understands your notation. It is the only thing you need. Of course, it is very easy to guess that, for me, say, that A minus B in your notation means this thing. Doesn't matter which symbol you prefer. Lemma 2. Lemma 2 says that the following statements are equivalent to each other. I say that A is a subset of B if and only if the intersection equals what, by the way? What is the intersection of A and B when A is a subset of B? Let's make a diagram, but please notice that a diagram proves nothing. What is the intersection this way?
It's A.
Of course. And I want to prove that this condition is equivalent to this one. And what is the intersection of these two sets? What is the union of these two sets? If A is a subset of B, what is the union?
It's B.
B.
That's B. Why this lemma is so useful? Because it allows us to replace inclusion by equality. And for equality, we will have a useful list of identities, which are recommended, of course, to be used in your proofs. But first of all, let's prove this statement. At first, I want to infer the second one from the first one. I am given that every element of A is an element of B. I want to prove that this set equals A. You know that in order to prove an equality, you need two inclusions. X equals Y, if and only if X is a subset of Y, and vice versa, Y is a subset of X. Do you agree?
Yeah.
We have proved it. Okay. So here I need two inclusions. But the first inclusion from the left to the right is already known to us according to lemma 1. So by lemma 1, the left-hand side is included into the right-hand side. But YA is included into this intersection. Why is it so? Let's use the definition. By definition, in order to prove it, I need that if X is an element of A, then X is an element of the intersection. That is, X is an element of both sets of A and B. Let's check it. Assume that X is an element of A. Then, of course, X is an element of A. Don't you agree?
Yes.
That's trivial. But also, X is an element of B. Why? By our assumption. Our assumption says that every element of A is an element of B. That X is no exclusion. So I see that every X from A is also from A and from B. So this X is an element of the intersection. Hence, every element of A is an element of the intersection. That means that A is a subset of the intersection. So I have proved both inclusions. Whence the equality follows. Is it clear?
It is.
The second one. From the second, derive the third one. From 2 follows 3. Assume that I am given with the following fact. The intersection equals A, and I want to obtain that the union equals B. How is it possible to obtain this result? As usual, the inclusion A is included into B follows from lemma 1. B is a subset of the union. But why A union B is a subset of B? Okay, let's consider any X, which is an element of the union. If X is an element of the union, then by the definition of the union, X is either an element of A or X is an element of B. Here we have two cases. But we know that if X is an element of A, then by our assumption, A must be an element of the intersection. By assumption, in the first case, X is an element of the intersection, or either it is an element of B. But if X is an element of intersection, it is still an element of B. So in both cases, X is an element of B, whence X is an element of B. So every element of the union is an element of B. Is it clear? Is it clear? Or do you have any questions?
Clear.
Clear, that's clear. Okay, and the last one, we want to derive the first statement from the third one. Assume that the union equals B, and I want to prove that A is a subset of B. It's also very easy. If X is an element of A, then of course by lemma 1, okay, there is no need to consider any particular element. We know that A is a subset of the union by lemma 1. The union equals B by our assumption. And of course, if it equals B, it is a subset of B. But inclusion is transitive if we have proved it. If X is a subset of Y and Y is a subset of Z, then of course X is a subset of Z. That's it. A is a subset of B. Is it clear?
Excuse me, could you please explain previous one again?
The previous one. Which implication? Is this implication clear?
Yes.
This one?
From here to below. From
This
definition to by assumption.
This is by assumption. You know, A equals intersection. So if X belongs to A, then it must belong to the intersection. And this one follows, say, by lemma 1, from the fact that if X is an element of the intersection, it must be an element of A. Here we have that X is an element of A and of B. And of course, that means that it is an element of B.
Yes. Thank you.
So I have two cases, and in each case, I have that X is an element of B. Hence, it's always true that X is an element of B. So I hope that's clear. This third one, is it clear?
Yes. Yes, thank you.
Okay, thank you for your question. We have proved the following statement. A is a subset of B if and only if the intersection equals A and the union equals B. And this is quite interesting, in fact. Why? Let's compare this to some other relations known to us. X is less or equal than y. Let's speak about naturals. X is less or equal than y if and only if the minimum equals what? X is less or equal than y if and only if the minimum equals what?
S.
X, of course. And
X.
the maximum?
Y.
Aha! So we see that somehow this intersection corresponds to minimum and union corresponds to maximum. Do you know what the greatest common divisor means? The greatest common divisor. After all, you have a number theory course.
Yes.
The minimum of the prime powers, something like this.
Of course, you may define it this way for non-zero numbers. Do you know this symbol? X divides y.
Yes.
X divides y. If x divides y, what can you say about the greatest common divisor?
It's equal to x.
Yes.
And the least common multiple, if x divides y, it is y. So you see that union is somehow similar to maximum and least common divisor. And intersection is somehow similar to minimum and the greatest common divisor. So that's interesting, I think. Of course, we have to develop this analogy more thoroughly. And now I'll state the following theorem, whose statement is also very well familiar to you, I hope. But anyway, let's state it. At first, we shall define a new operation. Assume that some u is fixed, some set is fixed. It is fixed, that means that we don't want to mention it every time. Assume that some u is fixed and a is a subset of that u. Say, a typical situation of this kind is as follows. You are studying subsets of natural numbers, and then u is just the set of all naturals. Assume that some u is fixed and a is a subset of u. Then we define this set, which is denoted by a overlined as u minus a. That is all elements of u which do not belong to a. And this set is called the complement of a to u, say. So if some u is fixed and we are only considering subsets of that u, you may consider complements. That is all elements of u which do not belong to a. If this one a, the complement is of course here. Is it clear?
Yes, it is.
Okay, and now we may state the following theorem. It has a proper name. Set algebra, the set algebra identities. the set algebra identities. For each U, for every A, B, C, which are subsets of U, we have the following. First, some statements, in fact, do not depend on the universe, on this U. By the way, this U is usually called the universe. Please, don't think that this U is a set of all sets or something like that. That's not possible. This is some local universe. So every set you want to consider this time is a subset of that U. Like in a situation when you want to study subset of natural numbers and U is just the set of all natural numbers. So our theorem says the following. A intersected by B equals B intersected by A. The same for the unions. So these operations are commutative. You may change the order of operands. Also, you have associativity laws, so you may freely regroup them. A intersection B intersection C is the same as A intersection B intersection C. And the same result holds for the union. Is it clear?
Yes.
Idempothy law. A intersected by A equals
A.
Of course. A union A equals A.
A.
Absorption laws. A intersected by the union of A and B equals A.
A.
These are just elements which are in A and in the union. Of course, every element of A is in the union. So we have this thing. This is just a rephrasing of the fact that A is a subset of the union. You know, if X is a subset of Y, then the intersection equals X. And likewise, we have a dual result. The union of A and this intersection equals what?
A.
Still A. So B is somehow absorbed. Absorption laws. 5. What else? The complement of the complement, double complement, is what?
A.
It is just A. 6. Distributivity laws. A intersected by the union of B and C equals A intersected by
A together with B.
and dually A union B intersected by C is what?
A union B intersected with A union C.
That's it. De Morgan's laws. De Morgan's laws. De Morgan's laws. The complement of the intersection equals
U.
the union of the
U.
complements.
Oh.
Just that. The complement of the union equals the intersection of the complements. 8 constants. A intersected by the empty set is? What are the common elements of A and the empty set?
Empty set.
The empty set. There is no such elements. If you take the union, A won't change. That's A. If you intersect A with the universe, you know A is a subset of the universe. Hence, it would be just A. If you take the union with the universe, you will obtain the universe itself. The complement of the empty set is the whole universe. The complement of the universe is empty. And the last one, the union or the intersection of A with its complement is? And the union is the whole universe. So that's it. It is beneficial to memorize these statements. What if I want to prove any of this? In fact, the most sure way to prove it is to apply logic. For example, let's prove the first De Morgan's law. I want to prove that every element of this set is an element of this one and vice versa. So this proof won't give us any new information, but just express the properties of logical connectives in set theoretic language. So assume that X is an element of our union. So when X, if X is not an element of, not union, but universe, if X is not an element of the universe, it does not belong to this one, to this set, nor it belongs to this one. So if X is in the universe, X is a subset of this set if and only if X is not a subset of the intersection. That means it is not true that X is an element of A and X is an element of B. According to our logic, according to truth tables, when the conjunction is false, when this conjunction is false, when it is not true that the conjunction of two statements, so please.
When it not be in one of the sets A or B.
Of course, when either statement is false, when this one is false, or this one is false. Is it clear?
Yes.
The conjunction is false if and only if either statement is false. This is due to logic. So that means that X is an element of the complement of A and X is an element of the complement of B. Hence, this result. So X is an element of this set if and only if it is an element of this one. Is it clear?
Yes. Thank you.
Yes.
And to finalize our lecture, let's see two easy examples. Example 1. Assume I want to prove the following statement. For each ABC, A minus B minus C equals A minus B union A intersected by C. I want to prove it. How is it possible to do so? The most boring, but the most sure way to do so is to consider a particular element of this set and prove that if X is an element of this set, then X must be an element of this one, and so on. But there is a much better way. I want to call in my identities. But the identities are about complements, so I need some universe. By the way, what if A is a subset, A and B are subsets of U? Then I say that A minus B is just the intersection of A and the complement of B. Is it clear? Here we have X is an element of A and X is not an element of B. If X is an element of my universe, that means that X is an element of A and the complement of B. So when I'm in some universe, the difference of two sets is just the intersection of first set with the complement of the second one. And this is very beneficial. So I want to take some universe. The only thing I want from the universe is that every set A, B, C is a subset of this universe. So I want to take the union of these three sets as the universe. Hence, of course, A, B, and C, every one of these sets is a subset of U. Is it clear?
Yes.
And then everything is really easy. Okay, here I have A minus something. It is just A intersected by the complement of this set. But this one might be rewritten the same way. Is it clear?
Yes.
The complement of the intersection is just the union of the complements. The complement of the complement
Is the set.
And now I want to apply distributivity. It is just A intersected by not B or B overlined, union A intersected by C. That is A minus B union this intersection, which is exactly my right-hand side wanted. Is it clear?
Yes, it
Yes.
is.
Yes.
And another example deals with changing inclusion to equality. Example 2. If C is a subset of A and C is a subset of B, then C is a subset of the intersection. If C is a subset of A and C is a subset of B, then C is a subset of the intersection. Okay. Of course, it is not hard to prove it by considering elements. But what does it mean that C is a subset of A? That means that the intersection of C and A equals what? C of C and A equals what? Equals C. And likewise, the intersection of C and B equals C. And here I want that the intersection of C and this set equals C. Okay. And now I have the following. C equals C intersected by A. This is by my first equality. Is it clear?
Yeah, clear.
And now let's replace this copy of C according to the second equation. I have this thing. By the way, it is not very good way to proceed. First, let's start with the second one. If we start with the second one and then proceed to the first one, we will obtain this thing. And now let's apply associativity and regroup these sets. So C equals this set. So C equals this set, which is what I need. Is it clear?
Yes.
So this way I may obtain a lightweight, algebraic, clear style of proofs without considering elements, but just rewriting some terms according to our identities. In a sense, this set of identities is complete. So every other identity, which is always true for these operations, follow from these identities. And if you come across set inclusion in your theorem, then you may easily replace it. By equality, and then apply the identities. Any questions, please?
Yes, excuse me. You was explaining the general form, and you denoted by a star. Could you please explain that again?
The general form of the set union. Okay.
Yeah.
The main idea is as follows. Every set consists of sets. You know, everything is a set. That means that every set is a set of sets. The union of a set is the set of all elements of the elements of this set. So X, by definition, X is an element of the union of A if and only if X is an element of some element of A.
If and only if, could you please repeat it again?
If and only if X is an element of the union of A, if and only if there exists some element of A, there exists some Y, which is an element of A, where X belongs to. So this is the set of elements. This is the set of the elements of A. X is an element of the union if and only if X is an element of an element. If you depict a set as a graph, as a tree, say A has some elements, Y1, Y2, Y3, and probably infinitely many other. This also has some elements, x11, x12, x21, x22, x31, and so on. What is the union? The union is this set. The set of elements of elements. Why this arrow represents being an element, of course. Why this one holds? That's quite clear. What does it mean that X is an element of this union? That means that there exists Y such that X is an element of Y according to the general definition, while Y is an element of this set. But this set has exactly two elements. So that means that there exists Y such that X is an element of Y and Y either equals A or Y equals B. So we have two possibilities. Either there exists Y such that X is an element of Y and Y equals A, or there exists Y such that X is an element of Y and Y equals B. But that means there exists Y which equals A. So Y is A. That means that X is an element of A, and this one similarly means that X is an element of B. So X is an element of this two-set union. Is it clear?
Yes, it is. But another question is this elements of an element. Okay, and is it possible to go further? Elements of elements of an element.
More surely, you may take it two times.
And what does it mean? What is it for, actually?
It is for exploring the inner structure of your sets. In many constructions, this naturally appears. But of course, in the absence of these constructions in our particular lecture, we have to consider some artificial examples, of course. First of all, what is the union of the empty set? It is empty because there is no element in the empty set. It's not possible to see this Y, which would be an element of the empty set. So this is empty. What is the union of the singleton? X is the union of the singleton if and only if there exists some Y, which is an element of this singleton, such that X is an element of Y. That is, the only element of this set, the only possible value for this Y is the empty set. So that means that X is an element of the empty set, which is not possible. So the union of this set is also the empty set. But in general, the union of singleton equals A. So effectively, the union just cancels a pair of these curly brackets. By the way, why is it so? X belongs to this set if and only if there exists some Y, so that Y is an element of the singleton and X is an element of Y. But the only element of the singleton is just A itself. So Y equals A and X is an element of Y. That is, X is an element of A. So X is an element of this set if and only if it is an element of Y. That means that this is so. Okay. And now, let's see, for example, this set. Union of the union of the union of this set. What is it? the first application of the union cancels one pair of curly brackets. So this would be the union of this set. This, the second application cancels another pair of curly brackets. So this is the union of the empty set, which is empty. Is it clear?
Till here, yes, but what's the union of a singleton with one curly brackets? It's empty?
The union, so please repeat, the union of the union
Of a singleton. For example, it sets A. No, A.
of A?
Yes.
Okay. Let's
It's
consider the inner part. This is the union of A. For the first application cancels our curly brackets, and the later, all the later depends on A. What's A? So in general, I can't say more because I don't know what A is.
What do you mean by A can be? What can A be?
What can A be?
What can it be?
Whatever set. This statement, this one, is true for every A.
And what if A is just what if A has just one element? I want to understand.
Then it is a singleton. If A has just element B, then I will have what? At first, I will obtain this one, then this B.
Sorry for asking too much question, but what I want to understand, if we write union of this set B that you wrote, the one before you wrote B set
Of this one?
curly brackets, two curly brackets inside B, yeah, and this one is empty.
No, why? It's not empty. It depends on B. It depends on
Oh
B.
my God.
It depends on B. You just see. The first
What if we have a number?
If it is a number, okay. What does it mean? Union 3. It depends on what 3 is. So in order to compute this set somehow, to compute that means to say name all its elements. I need to know what 3 is. But I have not defined 3. In fact, I've said that 3 is some set whose inner structure is not relevant for us. We just don't define it. If you insist, I'll reveal this secret to you and give you the standard definition of naturals. It is as follows. 0 is just the empty set. 1 is the singleton of empty set. 2 is the set whose only elements are 0 and 1. 3 is the set of 0, 1, and 2, and so on. That is, 0 is the empty set, and the number n plus 1 is just n union the singleton of n. So every natural number is the set of all previous numbers. This way, this is just the union of 0, 1, 2, or 0, 1, 2. But this set is included into this one included into this one, so it is just 2. The union of 3 is 2.
Oh my God, thank you.
But then it is very interesting that if we start talking about this thing, which is no part of our course, by the way, as the union of n plus 1 is n, but what about the union of the infinite set of all naturals? It is interesting to see that the union of n is n. Why is it so? Okay, let's prove it. If some x is an element of this union, that means that there exists a natural number, say k, such that x is an element of k. But that means, according to our definition, that means that this x is a natural number itself. For every natural number is a set of all lesser numbers. So, hence, the union is a subset of n. And vice versa, if x is a natural number, then x is an element of number x plus 1, because every natural number is a set of lesser numbers. So I see that x is an element of x plus 1, where x plus 1 is a natural number. So x is an element of an element. So x is an element of the union. So this set n is included into the union of n. The union of n equals n. By the way, informally, you should always remember that the union in set theory plays the same role as limit plays in calculus. Union is just a limit, a supremum or something like that. So the set of naturals is a kind of limit. Union of naturals equals naturals, but for every natural number itself, that's not true. The union of 3 equals 2. 2 is an element of 3, hence, by the foundation axiom, 2 is not equal to 3. Is it clear?
Yes, thank you for
So
clarifying.
something like that, but it is still informal. Why? Because here I have our unfortunate words, and so on. And so on. So I have I need some form of recursion or induction here. But in order to define a suitable induction or recursion here, I have one more axiom and quite a good deal of some formal technical work, which I don't want to include into our course for it not be too cumbersome. Okay. Have I asked your questions?
Yes, thank you very much.
Thank you for the interesting question, for the interesting discussion. Any more questions, dear students?